This prototype is a hydroponic farm monitoring system. It monitors temperature and humidity and controls two alarm LEDs. The system uses a polling model with software timers. LED 1 is used for temperature alarms and LED 2 is used for humidity alarms. In this video, I will explain the code, show the compile results, show the serial monitor output, and demonstrate the LED alarm behavior. For the hardware setup, the DHT22 data pin is connected to Arduino D2. The temperature alarm LED is connected to D4. The humidity alarm LED is connected to D5. Each LED is connected to a resistor, and all components share ground. The sensors is powered from the 3.3 volt rail. The code assumes active high LEDs, so writing high turns an LED on. This project is separated into 5 code files. GPIO Deacon is reused from the earlier task and provides the CMSIS-based GPIO abstraction. DHT22 Deacon is a small sensor class for reading the DHT22 temperature and humidity data. The Arduino sketch contains the application logic. It stores the current sensor value, pulls software timers, checks threshold, and updates the LED states. This slide explains the GPIO layer. The first highlighted section shows get port group. It converts the ports letter A or B into the correct SAMD21 port group. The second highlighted section shows the direction setup. PMUXEN is cleared so the pin behaves as normal GPIO. Direct set makes a pin and output, and direct clear makes a pin and input. The third highlighted section shows output writing. Outset turns selected output bits on, and outClear turns selected output bits off. This satisfies the register level GPIO requirement while keeping the main application code easier to read. This slide explains the DHT22 sensor class. The first highlighted block sends the DHT22 start signal. The data pin is configured as output, pulled low, released high, and then changed back to input. The second highlighted block reads the 40 data bits. The code waits for each high pulse and uses micros to measure the pulse width. A long high pulse is interpreted as a 1, while a shorter high pulse is interpreted as a 0. The final highlighted block checks the checksum. If the checksum does not match, the reading stays invalid. This is the constant section in the main sketch. Demo mode is set to true for the video demonstration. This lets the program cycle through internal test values instead of waiting for the physical sensor to reach every alarm condition. The poll period is 10 milliseconds. The real sensor sample period is controlled by sample period minutes, with a default of 1 minute. In demo mode, the sample period is shortened to 8 seconds so that every alarm case can be shown quickly. The first hold constants match the task requirements. Temperature below 10 degrees, temperature below 4 degrees, humidity below 15%, and humidity below 30%. This slide shows a polling model. The loop function calls the sensor sampling timer, the temperature alarm timer, and the humidity alarm timer. After that, it waits for the 10 milliseconds poll period. The sensor sampling function adds 10 milliseconds to sensor sample timer ms every loop. When the timer reaches the active sample period, the code resets the timer and calls sample environment. This is the event-driven model used in the task. The firmware repeatedly poll timer, and each timer expiry becomes an event that triggers an action. For the compile section, when the code compiles successfully in the serial monitor, a new test scenario is printed around every 8 seconds, so that LED alarm behavior can be recorded clearly. For the first scenario, it's normal conditions, so both LEDs should be off. When the temperature is 8 degrees, LED 1 blinks at 1 Hz. When the temperature is 2 degrees, LED 1 blinks faster at 10 Hz. When humidity is 42%, LED 2 blinks at 0.5 Hz. When humidity is 25%, LED 2 stays on continuously. This demonstration all required alarm state for the hydroponic monitoring prototype. Thank you.